So why is it important to ensure that you have decent variability in your scores? Okay, let's go back to our electrician test example. So this is where we're getting a restriction of range as a result of our test items. So imagine that we've created our test and we've only simulated very easy tasks. So for something like changing a light bulb, it's the sort of thing anyone can do. You don't need to be an electrician. If we only had those sorts of tasks in there, then we're probably very unlikely to be able to differentiate between high and low skilled electricians, and this will restrict the range. Here you can see exactly what would happen. So we've got our novices, we've got our experts, but because we've created tests that are so easy, sort of changing light bulbs and so forth, both of them are scoring right at the top end. They're both scoring very close to 100. Therefore, we simply can't tell them apart because they're all squashed together up here at the top end. Okay, very narrow range of scores, where we really want the range of scores to go all the way from the worst score there all the way to the best score. Got a very narrow range of scores, that's no use to us. Okay, so that's a ceiling effect in that case. Okay, so the effect of this would be to suppress a correlation between the test score and job performance. Well, in fact, any correlation that we would look at involving the test. Here's another example of restriction of the range, this time because of our sampling. So this is if we only, say, recruited novices rather than experts, then the range of scores we would get would be just restricted to that novice range. Okay, so here you can see the range of scores we would get if we only recruited the novice electricians, rather than if we recruited both novices and experts, we get a much wider range. Okay, so that is, we're running a risk, if we're just going to test this using just novices, of getting that truncated score and therefore getting a restriction of range and therefore getting an underestimate of the true validity coefficient. Okay, so that would suppress the correlation if we had that restricted range. Okay, in terms of why restriction of range suppresses correlation size, you can see that in this illustration here, where you've got a big scatter plot with the full range there from -3 to +3, and if you analyse all of those dots, you find that the correlation between x and y in this case is 0.89. However, if we now restrict the range from between 0 and 1, you can see that if we imagine this part of the diagram as a scatter plot on its own, that immediately the clustering around the diagonal becomes less apparent. Basically the dots are more spread out relative to one another, and if you look at the correlation just for that section, it goes down to 0.51. So that's a restriction of range for you. Another important point is that because in correlations we're converting everything into a z-score, we're standardizing both measures, it means that the absolute values of the scores are completely irrelevant. So effectively you're throwing away the raw means and the raw standard deviations of both of your measures. Okay, so let's illustrate this with a little example. So I've made up some data here where we've got 7 people. Each person has done 2 tests. Okay, they've done measure 1, and this is their raw scores for measure 1. They've done measure 2. It's the raw scores for measure 2, so you can see person 1 has got a 9 for measure 1 and a 7 for measure 2. Person 7 has got a 2 for measure 1 and a 1 for measure 2. Right, if we do a correlation between measure 1 and measure 2, the correlation is 0.91. Okay, very high correlation, and that's not surprising because you can eyeball that data and you can see, look, people 1 to 3, they're getting high scores in both tests. Person 5 to 7, they're getting very low scores in both tests. That is, the measure 1 is highly associated, is highly predictive of their scores in test 2. Right, what happens now if we do a linear transform? We effectively take one of those scores, only measure 2, and we multiply it by 1,000. Okay, what you find is that the correlation between those two sets of scores doesn't change in the slightest. It remains absolutely identical, and that goes for any linear transformation that I would care to do. If I convert them into z-scores or t-scores or IQ scores, doesn't matter, it will not change the correlation between those two measures, because when we do the correlation we effectively standardise both scales. Another key issue that I've already touched upon is the fact that correlations only represent linear relationships, which is where the two measures vary in a directly proportional way to one another, as in a straight line relationship. If you've got your underlying relationship and it's not a straight line, it's some sort of curvy, wibbly wobbly thing, then the correlation coefficient will be a poor estimate for that relationship. Okay, in fact it might even tell you that there's no relationship there when there in fact is. So with these four scatter plots you can see here, they're actually all give correlation of 0.816. They all give you exactly the same correlation, but notice only the top one here is actually giving what we imagine a 0.8 correlation to be. The rest of them, there are a greater pattern in the data, but you see for this one here, we've got obviously a curved effect, so we're losing most of that information because we're looking only at a straight line. With this one here and this one here, they're two clear outliers which are also misleading us. So the take-home message here is that if you're looking at correlations like this, then sometimes it is quite useful just to have a quick glance at the scatter plot just to check that there's nothing weird going on. Another key issue: when you run a correlation in SPSS or anything similar, you tend to get a significance test thrown in with it. So this is it's an SPSS output for you, where that's the correlation coefficient there, and here is the p-value from the significance test, and that's the number of people who've been tested. The actual significance test there is technically it's a t-test, and all it's doing is testing to see whether this correlation coefficient, the one that you've obtained, whether it's significantly different from 0. The reason for all of this is that, of course, every time we do something in SPSS, we're usually only dealing with a sample. We're not actually dealing with the entire population, so we're actually only testing a tiny proportion of the people to whom this correlation is supposed to apply. Generally in psychology, we're interested in how two measures correlate together in general, so that is effectively if we, say, tested the entire population, so everybody on Earth. Okay, here's another human measurement example for you. Imagine you're hired to create a measure of surgeon competency. Okay, and this is what we might do. We go and find ourselves 50 surgeons, and remember we're recruiting 50 surgeons to have a good range of abilities and so forth. Then we're going to get them to do a test we've created, and maybe this test could be some sort of simulation. So maybe there's a rubber mannequin with realistic internal organs, and they've got to perform an operation on this rubber mannequin, and we measure how fast they are, and we also measure the quality of the outcomes. Then the third step is we see how they actually do in the real world. So we follow up each of these surgeons and document their real world patient outcomes and come up with a score of actually how good they are as a surgeon, and then we correlate that real world outcome with their test score in our simulator to see whether what they're doing in that simulator is that a good prediction of what they would do in the real world. Okay, so imagine we do all that and the correlation between the test score and the patient outcome rating is 0.7, so that we'd be pretty pleased with that. It looks like our measure can predict patient outcomes to a reasonable degree. Okay, so that is, our measure is measuring surgeon competency. Key thing is, we know that the correlation for our 50 people is 0.7, but what we really want to say is that correlation of 0.7, is that also true for everybody, not just those 50 people, but for every single surgeon in the world, including people who haven't yet become surgeons, who may not even be born yet. Luckily, it turns out for us that even a relatively small number of people from the population can give us a pretty good idea of what the real population correlation will be. For political opinion polls, generally they sample around about 1,500 people, and this usually can predict actual election results, okay, where I think the actual election results is a measure of the entire population of eligible people. It can predict those pretty closely, okay, so usually the error margin in opinion polls is around about plus or minus 3%. So what it means is that we can be reasonably confident that our estimate of 0.7 from 50 people will be some sort of reasonable approximation of the true population correlation. Okay, but the point is that there's going to be some sort of margin of error in this figure. It won't be quite right. Okay, but basically the more people you test, the smaller the margin of error. Basically the more people you test, the smaller the margin of error will be. So this is us sampling a large number of people. The more people we sample, the more that the estimated correlation from that sample will be closer to the population correlation. The more stable it will be as well. And if we only test a tiny number of people, it means that we'll still get an estimate of the overall population correlation, but it simply will be less accurate and it will be more unstable. Coming down to the p-value you get with the correlation, the question we're asking is how likely is it that you'll get the correlation you did if the real population correlation was actually zero, so effectively a null hypothesis. So, give you an example, if we get a p-value of 0.05 with a correlation coefficient of 0.8, it means that there's a 5% chance that the population correlation you're trying to estimate is really zero, okay, where that error you've made is a result of sampling error. Is the population correlation actually zero? Okay, is the difference between your estimate and the real thing, could that be down to chance or not? What this means is if we've got a really large correlation, very easy to detect it as being different from zero. So that is, we don't need so much sensitivity, we can get away with a much bigger margin of error. However, if we're looking for a very small correlation, we need a lot more accuracy to detect it as being different from zero. That is, we need to test more people, simply because it's closer to zero. So here's our population. Imagine this is a situation where that's our population correlation. It's not zero, it's a, what would that be, 0.2, 0.3. Okay, we test a small number of people. It gives us an estimate which is roughly in the right ballpark for the population correlation, but not spot on. However, you can see it's got a big margin of error because we've only tested a small number of people. That margin of error does include the population correlation. Okay, but it's the estimate itself is fairly inaccurate. Okay, we start now testing a larger number of people. The effect we get is we're going to get an estimate which is much closer to the population correlation with a much smaller margin of error, much smaller confidence interval. Now let's look at a situation where we've got a population correlation which is very, very close to zero. So what that would be 0.1 or even less. Okay, it means that if we only use a small number of people with a resulting large margin of error, that larger margin of error will include zero, and therefore makes it impossible to reject the null hypothesis that the population correlation actually is zero. Because of course, remember, in real life we don't actually know exactly what this population correlation is. Okay, so essentially, if that margin of error includes zero, then it's not significantly greater. Then we say it's not significantly greater than zero. Okay, that's the very definition of a significant difference. However, look at the same population correlation, and now if we test a whole raft of people, what we're getting is a much smaller margin of error, a much smaller confidence interval that now doesn't include zero, and therefore, even though that correlation estimate is very, very small, it's still significantly greater than zero. Let's have a look at the opposite situation where we've got a very high correlation. Okay, so this is what this means is that even if you use a pretty tiny sample, you can get away with a large margin of error because you're so far away from zero. Okay, so that's why if you've got a big correlation, you can test a small number of people and it will still come out statistically significant. Right, this doesn't mean that you don't necessarily want to test lots and lots of people if you've got expecting a high correlation. If we test lots of people, we don't actually need that large sample to get the correlation estimate as statistically significant, but it's still the case that it might be an advantage if we want to know exactly what the magnitude of that correlation actually is. If we want a really precise measure of exactly how big the correlation is, we still might want to test loads and loads of people, even up in the higher ranks there. Okay, but if all we're interested in doing is seeing whether it's statistically significant or not, then we don't actually need to test that many people. So what's the practical consequence of all of this stuff? Well, the practical consequence is when you are doing your validity study, at some point you're going to have to sit down and work out how many people you think you're going to need to test. And the way you can do that is look at previous research, look at people who've done similar things, look at effect sizes that they found. And you can actually use a handy formal technique called paraanalysis, where it involves using formulae or downloading some free software from the internet, or even just looking up tables. And paraanalysis allows you to work out exactly how many people you need to test to be able to detect a particular size of correlation as being statistically significant. We need the following numbers of people. First of all, large correlation, so that's 0.5 correlation, that's just sort of rule of thumb. You'd need 28 people at minimum to get that to be statistically significant at the 5% level. For medium correlation, 0.3, you need 85 people. And for a small correlation, 0.1, notice now that the numbers are really ballooning out. You need about nearly 800 people to detect a small correlation as being statistically different from 0. And if you need to do a paraanalysis, so for example those of you who go on into honours and so forth or do further research, I can point you towards this reference here, which is a handy introduction and includes lots of these sorts of tables, not just for correlations but also for all other sorts of inferential statistics, t-tests, chi-squared tests, f-tests, all that sort of thing, which might come in very handy for you. Another issue I want to cover is the difference between the practical importance of a correlation size as opposed to its statistical significance. So essentially I can get a correlation and it could be statistically significant. That doesn't actually mean it's necessarily an important correlation. I'll give you an example of what I mean by this. Imagine that you're a clinical psychologist and you want to see whether the number of hours spent by a client participating in a clinical intervention designed to reduce depression is actually correlated with their depression levels after the intervention. Imagine you go and you find 1,000 people and you test the two things and you find a correlation of -0.15 between hours spent in the intervention and depression levels. So essentially, yeah, the more hours you spend, the less depressed you end up. And that's statistically significant, okay, because you've tested 1,000 people. Okay, so it's different from 0. That's not the question. The question is it still something that we necessarily want to recommend? So in reality, we'd probably be pretty disappointed by this result, because even though it's significant, it's actually a trivially small effect under these circumstances. So that is, yeah, you can spend hours and hours and hours in this intervention, and yeah, it has a real effect on your depression, but it's a tiny effect on the depression. So that is, there's probably other better things you could try first. Okay, so that is, the intervention is statistically significant, but it's not practically important. We can't actually provide any rules of thumb as to what counts as important or not important overall, because this depends entirely on the very specific context, on the consideration, so you have to do this on a case-by-case basis. But it's a case in clinical psychology, this is what I've been calling practical importance. You'll often see in the literature referred to as clinical significance to differentiate it from statistical significance. Finally, there's loads and loads of different types of correlation you can get. In this course I'm going to talk about two ones. So first one, Pearson's R, the most common one. It's a parametric correlation, so that means it's analysing interval level data, and it requires a few assumptions, such that, like for example, that the variables must be normally distributed, and it's very sensitive. However, if you find that the assumptions are violated and you can't do anything about it, then there's an alternative, which is Spearman's rho, which is non-parametric. That means the variables don't need to be normal, and they can be on an ordinal scale of measurement. That is, all it's doing is analysing the rank order of the data, not the intervals between the data points. Okay, and this means it's less sensitive, but you can use it in more situations. Okay, so the protocol here would be if your data are appropriate for a parametric test, then use Spearman's R. If there's some problem with normality, then try and fix it up first of all using non-linear transformations, so more on that in the lectures. If that doesn't work, then go ahead and use non-parametric Spearman's row instead. Right, I hope that all makes sense. If you had any questions about this online presentation, please ask your tutor, and good luck.